Bismillahir Rahmanir Rahim. In the name of Allah, the Merciful, the Beneficent. This is the 7th lecture of the course on Introduction to Statistics for Muslims. As we have been discussing, not all types of knowledge are useful, and yet having accurate and correct knowledge is very, very important. The shaitan deceived Adam alayhi salam by providing him with wrong information. Also, Allah Ta'ala sent Harut and Marut to teach certain types of knowledge which were very harmful, and the angels told the people that you should not learn this because it will cause harm, but the people refused and they taught them. So this statistics is potentially a very dangerous type of knowledge. It can be used to make things appear as objective facts about reality which are not true. So one of the objects of our study, the intention, is that we will protect the ummah from the harms that can result from false manipulation of the data. This kind of false manipulation has been documented in a book called The Confessions of an Economic Hitman. In the previous lectures, we have looked at various techniques for summarizing the data. At this point, we will be looking at a particular technique called histograms, and the histograms are a much more accurate and faithful representation of the data. In fact, done properly, they can provide almost the exact picture of what the data is. So in that sense they are quite useful. So we will learn how to make and interpret histograms in this lecture. The simplest case of a histogram is one that we have already seen before. This is the highest data set for household size. There were 127 households in the sample for a particular city. So each of these households have a certain number of people. So we list for each household how many people are contained in this household, and this list is pictured in this table. The table is a 8 by 16 table, so it has 128 entries. The last entry is empty because there are only 127 households, and each of the other cells contains a number which indicates how many people in that particular household. These numbers have been sorted, so you can see that the first 4 numbers are 1, which means that the 4 of the households have 1 person in them, and then the next 8 households have 2, so there are 8 households with 2 people each, and so on. This data we've already seen before, and basically the histogram graphs for each number the number of households which have that number of people in them. So the histogram provides a complete picture of the data. On the right hand side we have listed the data. There are 4 households of size 1, and in the histogram we see the picture that size 1 has 4 households contained in it, and then size 2 has 9 households, meaning that in our original sample of 127, 9 of the households are such that they have 2 people living in them. And similarly, for each size we list the number of households of that size. When we look at the histogram, it has a bimodal appearance. The 5 is a mode and 7 is also a mode. We did some analysis of this data set earlier. The point of this presentation is to show what a histogram looks like. There is one problem here, that the household size is a discrete, so it's either 1 or 2 or 3. It's not a continuous variable. So if you have continuous variables, then the histogram will not work, because each number will have only one country associated with, or one case associated with. So this picture, which shows how many households belong to one category, will not apply, because each category will have exactly one element in it. So the case where the data is continuous has to be treated somewhat differently, and this is what we turn to next. So now we look at how to make a histogram for a continuous data set. This is a data set again we have examined earlier. This is the GDP per capita in terms of purchasing power parity in constant US dollars in 2005, and we have listed all of the countries. I think there are 138 of them, and their GDPs. These are available in a spreadsheet. We have listed the GDPs for 4 decades: 1980, 1990, 2000, 2010, and we're only going to concentrate on the 2010 numbers for the moment. We can't put all of the 138 countries on this slide, so we just put the bottom 6 and the top 5 just for the sake of illustration, and also so the student can understand what kind of data we are working with. So for each country, the spreadsheet lists the number, which is the GDP per capita. The richest country in 2010 is Luxembourg, which has $68,679 per annum of income, measured in US dollars 2005 and converted in terms of purchasing power parity. This data has been sorted by the incomes in 2010. Now the question is how we can make a histogram of this data. So the trick is to create categories by making what are called bins. So we consider all incomes between 0 and 5,000 to be one category, and then between 5,000 and 10,000 to be the second category, and then between 10,000 and 15,000, and so on. So we make bins of size 5,000. Each bin goes from one number to the next higher up, and so now there are a small and finite number of bins, and then we just count how many countries belong to a particular category or a particular bin. So if we look at the counts in the columns, in the last column, 2010, we have 53 countries which are in the range from 0 to 5,000, and 19 countries in the range from 5,000 to 10,000. And similarly, for each category, we have a number which shows us how many countries fall into that range. So now we have a data which is quite similar to the household data, in that for each category we have a count of the number of countries which fall in that category, and now we can plot it just like we did earlier. So we can create a histogram. The same data that was presented in a table in the last slide is now put on a graph, which is the histogram for this data. It is the GNP data for 2010, the first thing to note is that there is an outlier, that was the Luxembourg. It has income of 768,000, and you can see it at the very end. Actually, it's in the bin which is between 65,000 and 70,000, and there is exactly one country in that bin, and you can see the small bar, the purple bar, which shows that there is one country in the range between 65 and 70. But because we are going up all the way to 70, the rest of the data is very compressed, and so we have a large number of countries, 53 of them, in the bin which is marked 5,000, and that's the largest bin. And then at 10,000 and 15,000 we have 19 and 18 countries. At 20,000 we have a very small bin. If you look at this data, it suggests that there might be two types of countries. There are the poor countries, which are clustered between 0 and 15,000, and then at 20,000 this set of countries ends. The data is actually bimodal, and then we have these rich countries which are going from 20,000 onwards and above. So because of the scale, it's not too clear, but basically one can think that this histogram is showing us that there are two types of countries, the rich countries and the poor countries. In this slide, the histogram of the previous slide has been copied, but the two areas, the rich histogram and the poor histogram, have been separately marked just so that the student can see that there are actually two different histograms here. The rich countries have their own histogram and the poor countries have their own. One issue and one problem is that the bin size for the rich countries is different from the bin size for the poor countries. As it is, the one category going from 0 to 5,000 contains 53 countries, and that's really too large. What we would like to do for the poor countries is to make the bin size of about 1,000 or smaller, so we can see what's happening, because a lot of countries are concentrated in a very small range. The same is not true for the rich countries. The rich countries are widely separated in income, so the bin size of 5,000 is suitable for the rich countries. So in the next few slides we are going to look at experimenting with changing the bin size so that we can see more detail about the distribution of these countries. The previous histogram shows that there is a natural break at about 15,000. So in this histogram we look at the countries which are lying between 0 and 15,000, and so for this purpose we look at the bin size of 1,000. That's so that we can see more clearly what is happening. And if you can look at this histogram, so you can see that there are perhaps divisions within the poor countries. There are the extremely poor countries which are below 7,000, and then sort of moderately poor countries which are going from 7,000 to 15,000. This diagram again looks a little bit bimodal, and it reveals that there is a lot of variation within this range of poor countries. So again, this provides us with a clue to reality. When we do analysis of levels of development or levels of wealth of countries, we might want to distinguish between the rich and the extremely poor and the intermediate poor, because they might have different types of mechanisms associated with their economics. So as usual, the data furnishes a clue to reality, and then to acquire knowledge we have to follow up these clues and study reality. The previous histogram shows that there is a natural break at about 15,000. So in this histogram we look at the countries which are lying between 0 and 15,000, and so for this purpose we look at the bin size of 1,000. That's so that we can see more clearly what is happening. And if you can look at this histogram, so you can see that there are perhaps divisions within the poor countries. There are the extremely poor countries which are below 7,000, and then sort of moderately poor countries which are going from 7,000 to 15,000. This diagram again looks a little bit bimodal, and it reveals that there is a lot of variation within this range of poor countries. So again, this provides us with a clue to reality when we do analysis of levels of development or levels of wealth of countries. We might want to distinguish between the rich and the extremely poor and the intermediate poor, because they might have different types of mechanisms associated with their economics. So as usual, the data furnishes a clue to reality, and then to acquire knowledge we have to follow up these clues and study reality. Just to repeat and clarify the point made in the previous slide, we have put the two histograms side by side. The histogram with bin size 300 is on the left, and the histogram with bin size 1000 is on the right. Both are the same histograms that we have looked at before, and as you can see, the histogram on the right is a little bit more smooth and seems to show a pattern in which there are two countries and two types, the very poor countries and the poor but not so very poor countries. On the left hand side with bin size 300, these patterns are not so clear. There are many gaps. What we say is that the picture is very jittery, and so it's less easy to interpret. Now we consider what happens when the bin size is too small, when the category. We looked at the poor countries and we saw that 1000 is a reasonable bin size. If we divide countries into categories from 5,000 to 6,000 and 6 to 7,000, this produces a reasonable picture of the distribution of the data. The histogram provides information. However, the same bin size of 1000 is too small if we look at the richer countries. So here the rich countries are the ones which go from 25,000 up to 40,000, and they are pictured in this histogram. But the bin size has been chosen to be too small. The bin size is again only 1,000. So we have a category from 26 to 27 and 27 to 28. As you can see, most of these bins have only one country in them. So if there is any pattern in the data, it is not obvious, because each point is being plotted separately. Basically, the pattern emerges by looking at combinations of points, and here there are a few combinations, but very few. There are a few categories which have 2 countries, and one category which has 4 countries in it, but mostly every bin is either 1 point or 0 point. This is always what will happen if we make the bin size too small. If we make the bin size small enough, then every point will be in its own bin, and there will not be the patterns which are contained in the point will not be visible to the eye. When the bin size is very small, then basically each point is represented as a rectangle within its own bin. There is only one point, so each point is pictured separately. This is very similar to a dot plot, where every point is represented exactly separately, and here we just provide a comparison of the dot plot with the histogram. So you can see that in the dot plot you can see some clusters as well, and these clusters are highlighted in the histogram. Basically, in the histogram, when there are a few points that are close together, then they pick up some length, and you can see that highlighted. But mostly in this particular histogram, because the bin size is too small, every point has its own rectangle, so every point is represented by a rectangle. There are only a few points which are close together, so then they come within the same bin, and therefore they add to the strength. So there is not much difference between a dot plot and a histogram when the bin size is too small. However, when the bin size becomes big, then a lot of points fall within each bin, and then the patterns which are in the points are much more clear in a histogram than they are in the dot plot. As we have seen, the bin size of 1000, which is quite suitable for poor countries, is not suitable for large countries. And so now we look at the rich countries going from 15,000 to 60,000, but we use the bin size of 5,000. So now we are looking at the rich countries, but we have the first group is going from 15,000 to 20,000, and there are 3 countries in it, as you can see from the graph. The second group is going from 20,000 to 25,000 GNP per capita, and that has 9 countries in it. And the third group has 7 countries in it. That one goes from 25 to 30, and so on. So basically what we have done is that instead of looking at the bin size of 1000, in which we got only one country in each bin, more or less, we have increased the bin size, and now each bin has a lot of countries. By doing this, we see that there is a pattern. This pattern was not visible when the bin size was too small, but now when we have made the bin size large, then we see that there is a clear distribution around 30,000. Actually this looks a little bit bimodal, but it's not necessarily true. More or less there is a small blip, 2 countries missing in the middle. If these 2 countries were if there were 2 more countries in this range, then this would be a standard unimodal distribution. It does show a little bit of skew to the right. It's not symmetric, it's not balanced on the side of the middle. The portion on the downside is small, and the portion on the right hand side of the center is elongated, is going out longer, so it's skewed to the right. So we have examined a lot of histograms for GNP per capita, and what have we learned from this exercise? One of the things we have seen from the histograms is that there is a bimodal distribution. Bimodal distribution is a sign that there are two groups. One is a group of poor countries and the other is a group of richer countries. Also the distribution is right skewed, which means that there are a few countries which are extremely poor, extremely rich, and there is a large number of countries which have middle income or low income. Actually, you can separate the two groups and you find the same phenomena. Within the poor countries, there are a few countries which are rather rich relative to the poor, and most are very poor. And the same pattern holds in the middle income and high income countries, that most countries have a moderate amount of income but a few are extremely rich. And the same pattern holds among populations as well. If you look at the incomes of the people within a country, the vast majority are middle income or poor, and a few people are billionaires and millionaires. And this is a sign of a right skew. One very important thing that we need to stress is that the patterns are just clues. That is, we made a division of the countries into rich and poor by looking at the histogram, but this is not actually the reality. This is not objective. One has to go and look specifically at the countries to make that decision. One has to look at the real world. For example, if it is considered that if somebody has $1,000 of income per year, then he is not poor. The poverty line is set at $2 a day with 365 days, so that was about $700 is considered to be the poverty line. So if somebody has $1,000 a year, then he is above the poverty line. So if a country has GNP per capita of 1,000, then it's technically above the poverty line, but this will depend on the distribution. If all the income is equally distributed among everybody, then everybody will have about $1,000. But it could also happen that there is only one person in the country who has all the money, and all of the others are extremely poor. In that case, this country is above the poverty line for only one person. Similarly, it could happen that a country has average income per capita of 5,000 or 10,000, so we could say that it's comfortably rich. But when you look at the real data, when you look at the reality, then you find that very few people have all of the money and most of the country is poor. So even though the GNP per capita is high, most of the country is actually below the poverty line. So this is one way in which the numbers can deceive us, but there are many other ways. There are, for example, countries in which people are farmers and they consume what they produce on their farms, and this because it doesn't go to the market, it doesn't get counted in the GNP. So one would consider that the country is very poor, but in fact all of the people are well fed. So there are many aspects of reality which are ignored by the numbers, and so we can't take the numbers as the final answer to any question. The numbers can provide some support to any argument that we are making, but they are by themselves never enough. We continue with our analysis of the GDP per capita PPP data in US 2005 constant dollars. We have seen that different income levels require different bin sizes. So now we introduce a variable bin size plot so that each range of incomes gets its own bin size. So in the range from 0 to 7,000, we have used a bin size of 300. Going from 7,000 to 15,000, we have used a bin size of 1,000, and then from 15,000 to 70,000 we used a bin size of 5,000. So now when you look at this graph, you see three groups of countries. So you could see that there are poor countries and middle income countries and high income countries on the basis of this picture. As I've said, the picture can be deceiving. So the picture is just a suggestion, a clue. The data hints that this might be the case. In order to confirm this or to disconfirm it, one has to go and look at the real world factors. Just to explain this graph further, we analyze how it was made and what it consists of in the next slide. This is the same picture as in the last graph, but I have marked out clearly how we have changed the bin size. So the first black line is up to the 7,000 mark, and the bin size is 300 here. Going from 7,000 to 15,000, the bin size is 1,000, and above that level every bin is 5,000. So the bin sizes are compressed. Actually, the picture is not in the right scale. That is the on the right hand side, the graph is much longer, but it has been compressed because the unit of measurement has become much larger. So one other thing about this graph is that it's not a proper histogram. In the histogram you have rectangles. Here instead of rectangles, I have just joined the points by a straight line. So this is not a real histogram, although it does have a similar function. Actually, we will consider more complicated types of histograms in the next lecture. So this is just actually, because the histogram is just to provide us with a picture of the data. So this picture is almost as good as the picture with the rectangular bars. So it doesn't matter very much exactly how you represent the points. The picture remains roughly the same. This situation where the scale of the data keeps increasing as the numbers increase is a rather common one, and so there is a mathematical trick that is used to deal with it. In the previous graphs we just used an arbitrary division, and we chose different scales at different bin sizes at different categories of income. One way to do this sort of automatically and smoothly and continuously is to use the logarithm scale. So instead of the GDP, if we take the log of GDP, then the scale keeps increasing continuously. So here I have plotted the log scale. If the GDP is 316, then the log in base 10 is 2.5. Quarter point difference takes it to 562, but then another quarter points of difference takes 562 to 1000. So the step size in the log scale is a quarter, but on the GDP scale this same quarter keeps increasing. This is same situation is shown in the graph, where a half a point difference on the x-axis translates to a very small difference in the initial part, going from 2.5 to 3.0. The blue line hardly rises. From 3.0 to 3.5 there is a more rise. From 3.5 to 4 there is even more, and similarly the graph of the log keeps increasing. That means that if we measure GDP in the log scale, then we will automatically achieve the kind of change that was made in the earlier graph. That is, as we go up the scale, the same step will measure a larger difference in the GDP, and so we will have larger bin sizes on the right and small bin sizes on the left of the graph, which is exactly what we did, except for the fact that this time we have a continuous function, and we don't need to arbitrarily decide what is the scale going to be at what point in the graph. So we'll now look at the log scale histograms for the GDP data. This is just like the variable bin size, but the variable bin size has been handled by taking logs. I have two plots here. One of them, in both cases, we're looking at the log of the GDP, and we're making a histogram for the log of the GDP of the 138 countries, I think it is. And in the first graph, on the left hand side, we have a large bin size, that's 0.25. Now the data looks like it's unimodal, really. It doesn't have a bimodal picture. You can't really differentiate between the rich and the poor countries and say that they are separated. Now they've gotten merged, because by taking logs we have reduced the big differences and we have shrunk them all to be on a common scale. So the log scale plot hides some of the complexity of the data, and it also brings out some features which are not apparent in the original data. The second plot on the right hand side is the same data, but the histogram is now the bin size is finer. It has been reduced to 0.1 or 1/10 instead of 1/4. So with this small bin size, you can see that the picture has become less smooth, more jagged. Data points are showing up clearly separately, and here you can see that perhaps there is some bimodality, or there are multiple modes. Maybe you can distinguish between the rich countries and the poor countries, or rich, middle income and poor. It's not so clear to tell because there are some random peaks in the data, and this is what happens when you have a fine bin size, a small bin size. Then some of the bins are small. Here every bin has there aren't any bins with just one country, except for at the very beginning, at the very end. Those are somewhat outliers. It's a little bit hard to interpret a log plot, and we will get more practice in doing that later. The only point here is that different types of ways of plotting the data can lead to different pictures, and there is no one objective correct picture. Different pictures are useful for different purposes, and there is no single unique objective way of representing the data, contrary to what is widely believed. So different types of pictures are useful in different arguments. To get more practice with histograms, we look at the histogram for the infant mortality in 2010. This is a group of 159 countries on which the data is available. The infant mortality is a number ranging from 2 to 120 in this data set, in which the number shows how many infants out of 1,000 die within some short period of time after birth. So you can see, for example, that the first bar is up at about 46 countries. So there are 46 countries in which the infant mortality is between 0 and 10. And that's a very good infant mortality. It means 990 or more infants out of 1,000 survive for the initial period of time. At the second bar at 20 is around 38, which means that there are 38 countries in which the infant mortality is between 10 and 20, and the third bar is at 15 or so, which means that in 15 countries the infant mortality is between 20 and 30, and then at 40 it goes down to 6 countries. So there are 40 countries in which the infant mortality is between 30 and 40, and then there is a jump between 40 and 50. Again we have 15 countries, etc. So if we look at the picture, it has two things which are clear from this. First of all, this is a bimodal distribution. It seems like there are two groups of countries, a group of countries in which there are good health measures, and these have infant mortalities not beyond 30. 30 is a pretty good number. It means that 97% of the infants survive. And then the second group of countries starts out from 40 and goes up to 120. So from 4% to 12% we have countries in which the health facilities are not so good, and so the infant mortalities are rather high. So we have bimodality. Again, this is a clue about reality. We might consider that there are some qualitative differences between these two countries, but in order to really learn what this data means, we would have to go back and find out that what are the reasons why the countries with low infant mortality have this. Is it because all of the births takes place in hospitals while there are few hospitals in the other countries, or are there some other factors? To really understand what this picturing is telling us, we have to follow up the clue that is given by the picture and to go and look at the real world situation which leads to this bimodality. The other feature that is clear from the graph is that there is a right skew in this. The graph is not at all symmetric, and in the right hand tail this means that there are few countries which have extremely high infant mortality. So but most of them have an average amount. If you are interested, Pakistan infant mortality in 2010 was 60, which is right around the middle of this graph. So it means that Pakistan is, for the sake of comparison, now we draw the histogram for the same data, infant mortality, but in 1970, and the histogram is drawn in the same way, but now the top value goes up to 210 and the bottom value is around 10. So actually infant mortality has decreased quite a bit in the 40 years from 1970 to 210. If you look at this graph, there is no really clear bimodality here. It seems like the countries are in a range going from small to high, but it's a continuous difference. It's not that there are two groups of countries. When you have two groups, then it is likely that there is some technique, some health technique which is in use in one country and not in use in the others. In this kind of a picture where there is no bimodality, it is just that maybe all the countries are using the same technique, but in some health facilities are available to 100% of the population, in some it's available to 90%, in some it's available to 70%, and so on. So it's a continuous graded difference between the countries. It's not that there are two different types of countries. So again, the data is giving us a clue to the data. We are just guessing that this might be the case on the basis of the numbers. The reality has to be explored in order to find out if this is really true. There is a little blip in the end. You can see that there are outliers. There are actually 5 countries which are in the end, and these 5 countries have been listed separately. And if you look at the 5 countries in 1970 with the 5 highest infant mortality countries, these are Bhutan, Sierra Leone, Yemen, Malawi and Afghanistan, then you see that in 2010 4 of these 5 countries reduced the infant mortality by a substantial amount, but in Sierra Leone the infant mortality was also reduced by a substantial amount, going from 195 to 121, but Sierra Leone remained one of the worst countries over this whole period. So it's interesting that even though medical facilities in Sierra Leone has improved substantially, the cut from 200 to 120 is substantial. At least 40% or so of the infant mortality has gone down, and that's a substantial improvement in 40 years. Still, Sierra Leone remains among the worst countries for infant mortalities, and so there are 2 facts that we learned from this, that about Sierra Leone, that although it has the worst mortality and it remains the worst among the worst countries over this whole period, nonetheless infant mortality has been going down. So even in the countries with very poor health facilities, infant mortality has been improving. So one has to find out what are the real factors which are causing this decline in infant mortalities. As a final example of histograms, we look at the life expectancy data for 193 countries for the year 2010. This is again taken from the WDI data set, World Development Indicators. So there are 193 countries in this data set, and for each country the life expectancy is the average life that one would expect to live if he was born in 2010. So obviously the first thing to note is that this is an estimated figure. You can't really know how long people will expect to live. It is based on what we observe about how long people are living today, and based on some ways to extrapolate from that. So at this point we will not discuss how one estimates life expectancies, but remember that when it comes to making arguments, this is something which one might need to look at, because those estimates will have their own errors and assumptions built into them. At this point we just look at the data, and we see that the histogram is more or less unimodal, so there is no indication that there are 2 different types of countries with different types of life expectancies. And furthermore, it is left skewed. Most of the data sets we have been looking at, the income data sets, they have been right skewed. They have been outliers on the right hand side, but here we find that this is left skewed. There are a few countries which have very low life expectancies, but most of the countries have average or moderate life expectancies. So these are the 2 main basic lessons from this chart. Notice that this is similar to the what the infant mortality data is telling us, in the sense that most countries have low infant mortalities and a few have high, because life mortality and infant mortality and life expectancies are opposites. If one has good health facilities, then life expectancy will be high and infant mortality will be low. So having good health or reasonable health facilities will lead at the same time to low infant mortalities, and a right skew in infant mortality corresponds to a left skew in life expectancy. So these 2 datas are giving us the same idea about health facilities in different countries. If we look at the same variable, life expectancy, in 1970, the histogram is quite different now, This time it looks bimodal. Furthermore, there are no outliers, and there is a slight left skew. One more interesting thing which is not obvious is that the scale of the data has shifted. The scale is just the range from the minimum to the maximum. In the previous graph, the life expectancy was starting at about 40 and going up to about 85. Here the life expectancy starts at 30 and goes up to about 75. So there is quite a difference in the sense that life expectancies have increased by about 10 years throughout the world, in the low countries as well as in the high countries. So that's quite interesting that there has been improvement in life expectancies throughout the world of about 10 years. Again, this is a interesting fact which is revealed by the data, but we cannot claim to understand it until we go to the real world and discover what is it that caused this increase. There can be many factors like better food and nutrition, or maybe it is due to better preventive health measures or better disease control. We don't know at this point which. There is in fact the possibility that some improvements in or changes in the way we statistically calculate life expectancy could also be responsible for this, although this is unlikely. Still, the source of this increase must be found in real world causes in order to really understand what the data is telling us. In addition, there seems to be the fact that this data set appears to be bimodal, and the later data set 2010 appears to be unimodal. So possibly there are certain differences that used to exist between countries. Maybe it was medical knowledge, or maybe it is some other factor, but this differences which bifurcated the country into two types appears to have been eliminated. Again, to really understand what's happening, we would have to refer to real world factors, which requires going outside and beyond just the numbers. So we will end this lesson with some concluding remarks. One of the things that looking at the data teaches us is that most data sets are not normal. Normal distributions have symmetry, they are balanced on both sides, the mean and the median is the same, and they have no skewness and they have no outliers. Most of the data sets that we have seen don't satisfy any of these properties, which means that the mean and the SD, which are the commonly used measures for summarizing data, are not very useful. The techniques that we have discussed here are actually both invented in the West and are in use in the West. However, they play a marginal role because implicitly it is assumed that most of the data is normal. Only every once in a while, if this assumption is thought to be violated, then these techniques are used. In our course, we are assuming from the beginning that the data will not be normal, so these techniques, which are of marginal importance in conventional courses, are of central importance in ours. In addition, we have redefined the role and the purpose of statistics, and we consider this as one piece of information, numerical information about the real world. The object of the game is always to find out about the real world. Numbers provide one possible way to learn about the world. It's not perfect, it's not exact, and it doesn't give us definite answers. This attitude is in contrast to Western ideas according to which numerical knowledge is exact and perfect and the best possible knowledge, and opinions are unimportant. In fact, our methodology suggests that the numbers are just clues, and it is more of our knowledge of the real world, which will often be subjective and qualitative, which will play a very important role in how we understand the statistical analysis. But the most important difference is the purpose for which we are learning statistics. Our purpose is not to make a living for ourselves, but rather it is to provide accurate information for the service of all mankind, because this is actually what we were told to do by the Prophet, that our lives should be devoted to the